Hi children, this is your Suvarna teacher. Children, in this video, we are going to learn the concept of hybridization and the formation of beryllium chloride and boron trifluoride based on hybridization. Let us see what is hybridization. Hybridization is the concept of mixing of atomic orbitals into new hybrid orbitals with different energies, shapes, etc. than the component atomic orbitals suitable for the pairing of electrons to form chemical bonds in valency bond theory. Children, hybridization is a phenomena of intermixing of atomic orbitals of almost equal energy are present in outer shell of the atom and their reshuffling or redistribution into the same number of orbitals but with equal properties like energy and shape. Children, this concept is little bit complex to understand, isn't it? Let me explain in a simple way through this small story. Children, once I was alone in my home. Suddenly, unexpected guest has came. I wanted to serve some snacks and drinks for them, but unfortunately, there was nothing to serve them. Only some fruits were there, and all are different fruits. I want to prepare some fruit juice with those fruits, but the fruits are not enough to prepare single fruit juice. Suddenly, I got an wonderful idea. I mixed all the fruits and prepared a mixed fruit juice and served them with the same taste. So children, hybridization is a concept just like mixed fruit juice. Different fruits are resembled or compared with different orbitals. In the story, there are different fruits. In our hybridization, there are different orbitals. By intermixing the orbitals, we can get the identical means same hybrid orbitals just like mixed fruit juice. These hybrid orbitals are identical and equal in energy and shape, just like the taste of mixed fruit juice. Even though mixed fruit juice is prepared with different fruit juice, the final result of mixed fruit juice will have the same taste throughout. These hybrid orbitals will give some same bond strengths to the chemical bonding. Based on this hybridization, there are three types of hybridization, that is sp, sp2 and sp3. Let us discuss sp hybridization with beryllium chloride example. As we know that beryllium electronic configuration is 1s2, 2s2. It is expected not to form covalent bonds, but it forms covalent bonds with chlorine. To explain this, an excited state is suggested for beryllium in which electron form from 2s orbital shifts to 2px level. Now the electronic configuration in excited state of the beryllium atom is 1s2, 2s1 and 2px1. Next, beryllium atom in its excited state allows its 2s orbital and 2pz orbital, which contains unpaired electrons, to intermix and redistribute to two identical orbitals. As per Hund's rule, each orbital gets one electron. The new orbitals based on the types of orbitals that have undergone hybridization are called sp orbitals. That means in s orbital there will be a hybridization or there will be intermixing of s and p orbitals. Before participating in the chemical bonding with chlorine atoms, the beryllium has prepared its own hybridized orbitals and it is ready to form covalent bonds with chlorine. The two sp orbitals of beryllium get separated by 180. Now each chlorine atom comes with its TpZ1 orbital and overlap. It is the sp orbital of beryllium, forming two identical beryllium chloride bonds. That is, both are sigma bond between one sp hybrid orbital and p orbitals, and the bond angle is 180 degrees. So there is a bond formation, covalent bond formation between beryllium and chlorine. The two hybrid sp orbitals are overlapped with the 3pz of two chlorine ions to form a sigma bond. So both the bonds are having same strength. Let us see the sp2 hybridization with beryllium trifluoride example. Boron trifluoride example. Boron has electronic configuration 1s2, 2s2, 2px1. As it has one unpaired electron 2px1, it should form only one covalent bond to give boron and boron trifluoride molecule. But we get practically boron trifluoride molecule. To explain this, it is suggested that boron first undergoes excitation to get electronic configuration, that is 1s2, 2s1, 2px1, 2py1. That means the electron which is present in 2s is shifted to 2py. As it forms three identical boron and fluorine bonds in bf3, it is suggested that the excited boron atom undergoes hybridization. So there is an intermixing of 2s, 2px, 2py, because these three orbitals are having only one electron each them, and these 2s, 2px, 2py orbitals and their redistribution into three identical orbitals called sp2 hybrid orbitals. That means boron, before participating in the covalent bond with the fluorine, it undergoes the sp2 hybridization, and the one s orbital and two p orbitals will intermix, redistribute and reshuffle their electrons and form three identical sp2 hybrid orbitals. For three sp2 orbitals to get separated, to have minimum repulsion, the angle between any two orbitals is 120 degrees, or at the central atom, and each sp2 orbital gets one electron. Now three fluorine atoms overlap their 2pz orbitals containing unpaired electrons. That means children, before participating in this covalent bond, boron as the central atom, it already have three sp2 hybrid orbitals. These three sp2 hybrid orbitals will orient or will place at the three corners of the triangle, and with these sp2 hybrid orbitals, the three 2pz orbitals will overlap, form three sigma bonds, and finally they form the covalent bond with the central atom boron. The three sp2 orbitals of boron that contain unpaired electrons to form three sigma sp2 orbital and p orbital bonds. So children, this is the example for the sp2 hybridization in boron trifluoride. We here three things comes off from a sp2 atom. That first one is shape, trigonal planar, and the shape of the sp2 atom molecule should be trigonal planar, and the bond angle is 120 degrees. Okay children, I hope you understand the concept of hybridization thoroughly. Children, in our next video, we are going to discuss about sp3 hybridization. Thank you children.